everybody. I'm happy to be here. I would like to thank, of course, the organizers for inviting me. It's such a pleasure to be here. And I will try to discuss with you, today to talk about, some problems that we have on symmetric group. So very simple questions, which turns out to be very tough in general. So this is a joint work with Sanjay Rangulam of Queen Mary University of London. You will find the main core of our result in this archive paper. And so let's move on. So, of course, motivating the story, I will do it in these two sections. First of all, the general problems, and then how this problem appears in theoretical physics. And this is in topological quantum field theory. So, yeah, so all of this will give us some motivation to understand this problem. And then that problem should be understood combinatorially first. And then after that, you may ask your question, how does it cost if you want to implement your solution? And that, of course, it's a computer science question. All right, and then we have more stuff, and I will then to a conclusion. So let me set a few basic definitions about, well, the symmetric group. This is the way that I will note it. It's Sn, that's a symmetric group of n objects, n being a positive integer. And a representation will be just an homomorphism from Sn to the general linear group of a vector space of dimension dim v. Well, you ask that this matrix should be invertible. And then the next thing that you wish is to have irreducible representations, and then are labeled by partitions. Yesterday, Jean-Douze have explained us very well what is a partition, so I can just, assume that you know better now what are partitions. So this is just a decomposition of an integer, a positive integer, into positive integers, such that summing them boils down to the first one. All right. So now the character of a given representation is nothing but the trace of that matrix. All right. So character of course, central elements, which means that if you conjugate your elements, it's still, that's the same object. And then now, if it's stable on the conjugacy class, you may wish to understand how are, conjugacy class of Sn. And conjugacy class of Sn are again labeled by partition of n. So what's the relationship? So a conjugacy class labeled by some mu is nothing but all permutation that has what we call the cycle type mu. In other words, you have to count, you have to do the list of all size of all the cycles of your partition, and you get, this partition. We will use two ways of representing a partition, either, this way, where you just list all parts, or, a number and its multiplicity. So here you have 2 ones, so I write 1 power 2. 2, 1, because there is a single part of size 2, etc. So, okay, as I said before, characters are stable on a class, on the conjugacy class lambda, so you can take any representative of that class to compute the character. And then what you should know is that character for Sn are integers, positive or negative integers. All right, so your character is labeled by 2 elements, by 2 partitions, one for the representation, the dimension of your representation, and one for the partition labeling the conjugacy class that you want to compute the character. So in that table that we call the character table for Sn, rows are labeled by ureps. That's a convention, of course. That's just a table. And columns are labeled by conjugacy classes. So this is for S2. That's the most simplest thing to see. So above there, this is my conjugacy classes. Okay. Partitioning 2, you have 2 ways of partitioning 2. Either you take 2 or you take 1 plus 1. So that's that sector. This is the label for representation. And inside this table, 1, 1, minus 1, and 1, these are the characters. Now pay attention that if you take at fixed row, you sum these number, you end up with 2. And if you take the other one, you end up with zeros. But these guys are positive integers, whereas what you have inside the table may be negative or positive. Pay attention also that if you do the same for columns, you end up with positive integers. Of course, if you have the positive integers there and there, if you sub everybody, that's a positive integer, of course. In fact, this happens for all the character table of Sn. So summing the characters along a row, that gives you positive integers, whereas characters may be not positive. And then do the same for columns, you end up with a positive integers. And you can do otherwise, you can go up above and you see the same feature. So the question is, how do you interpret these positive integers? Do you have a way of constructing them? If I give you two partitions, how do you come with these positive integers, which means how do you interpret those numbers here and there, as an object, anything? All right. In fact, when you do have a positive function like that, I'm taking here 0 and 1 because this is just a way of representing my initial data. I will use as entry of my function any binary words. And then if you have a positive function, what can you ask? You can ask a way of constructing, these numbers. Oh, I know, I was good. It came back alone. Great. Okay, so I find, you may ask the question, do you have another way, a bijective way, of giving me that f, that function, on a given entry? Can you construct it from the input? Well, so that's one question that we call combinatorial. You may ask also, how much does it cost to produce the solution computationally? Okay, so that's second questions. And you may ask first about this, the cost of deciding the positivity, when is it strictly positive or when it is vanishing, just 0. So that's question, a yes or no question. And you may ask also, well, how does it cost to compute the number for any number? So that's a second type of questions that you may ask. And this is, of course, things that you see in computer science, in particular in computational complexity theory. So this is the state of the art about, character table of the symmetric group. So computing the character by themselves, if I give you two partitions to compute a single character, well, if you look for a combinatorial rule to compute them, this is known since a long time ago. This is the Murnaghan-Nakayama rule. Okay, so in 1937 and then rediscovered by Nakayama independently in 41. Deciding the positivity is also known. These classes, perhaps some of you knows about it, perhaps other people doesn't know it. Doesn't truly matter. I will explain the type of class that I need in my talk, and this is just to say that this row is well under control. Okay, so it has been understood fairly well. Let's have a look about the row sum. So I'm fixing here a representation summing over all conjugacy class. This is today not known. To this number, the row sum of the character table of the symmetric group, nobody has an interpretation, a construction of that numbers, of these integers. And it's labeled, is known under the 12th problem of Stanley. Of course, Stanley was just, he was just recording all the difficult problem in his review.
Is non-negativity experimental or proven?
Neither proven, not experimentally. Yes, you can do tests, on the computer in increasing n, and you don't see it's still there, it's still positive, and nobody knows why. All right. So deciding the positivity, we don't know yet in which complexity class it is. We know computing them, that is in GAT P, but this is a really loose statement, if you want. Okay, we want more detail about that. So it's not, this is a closure, for expert, this is a closure of sharp P under subtraction. So you can express it as a difference of two functions, of two positive functions. But this is not satisfactory because you're still having an operation that you don't fully interpret. All right. What about the column sums?
Sorry, Joseph?
Yes.
So you said you can express it as a difference of two positive functions, but what are the properties of these functions?
Well, I will explain you. This is what we call sharp P. the Sharpie class.
So both computing both functions is in Sharpie.
Yes. GAP is the closure of Sharpie under subtraction. No problem, I will give you a crash course about it. All right, so column sums. Column sums are, well, the combinatorial rule are known. This is also a hold result by Schur and Frobenius. The column sum, so if I give you one conjugacy class, you sum over all columns. So this is what we call, no, you fix a column and you sum over all rows. This is what we call the column sums of the character table. It is known, as the Schur-Frobenius formula. So what is it counting? Is counting the number of permutations that squares to a given element of that conjugacy class. So you fix an element in the conjugacy class lambda, and you ask how many square roots this guy has in Sn. So this is what is counting.
So it's already non-negative, yeah?
Yes, this one is good. This one we know. This one, the column sum is good. So we know that it's positive and controlled, okay? What about its complexity class? So deciding the positivity, how much does it cost to determine whether or not you do have such a sigma, such a square root? So this is NP, and this is the only thing that we know so far. It's deduced from this. And because this now is exactly telling you that it's Sharpie as well. So if you have this one, you are very close to know how much it costs the computation. So this one is okay, but pay attention, I'm saying anything about the hardness of the computation, which what we call hardness in computational complexity theory. Is it exponential? Is it just polynomial? This is not say anything about it. So still this row is not totally satisfactory. The mathematics, the positivity is okay, we know that, but how much does it cost is still a bit open. The total sum, well, if you have this column sum, you just have to take the union of all columns to have the total. So this is the combinatorics is already is okay, is done. The two other things here is not yet okay. We don't know them. Okay, so that's the status for this thing, but what you have to understand better.
The total sum is just one number.
Sorry?
The total sum is just one number.
It's just one number, indeed.
And if we know it's positive, yeah, so it's, if I put...
Yes, if this one is positive, you know that this one will be, right?
No, I mean, this in the last row.
Yeah.
Is this first double.
This one?
Yeah. It's obviously just one number.
Yes, but you have to know, decide how much, you have to tell me, is it hard or not hard to know that number is positive or not?
I know it's positive.
Yes, you know that, okay, so you know already.
No, because it's a total sum, just one number.
Yes, but that number can be zero.
We know it's not zero because it's some permutation square of another permutation.
Yes.
It's really nothing. It's just one number. You don't. There's no questions about number. It's a big number like 13 or whatever you have. Yeah. No, it's positive. Yeah.
Do you mean it's for once you know that it's trivial for you? That's positive number.
You give a definition. It's clear. It's positive. Yeah.
No. Oh, hold on. Okay. So let me be clear. This one. This column here, of course, from here you know that it's positive, but it can be zero.
Yeah, no, but in the last in the last row, you have just one number, total sum.
Yes, even this one is everything is one number.
No, there's no parameters here, no lambda.
No, see, yes, you do have n. You have n as entry. So I give you n, Sn, the number of object. So I give you n, and you compute from that the sum of all entries of the character.
No, deciding it's positive, not computing. Deciding it's not negative.
Okay, so this is a bad notation, Maxim. Sorry. It's either deciding is strictly positive or equals zero. So
but this one number depending on n, we know it's for all n is positive.
Go down.
So yeah, so this one,
yes, exactly.
Yeah.
It's always positive.
It's always positive.
It's always positive. So in which case you do have a theorem tells you immediately that you have in constant time. So this part for you, it will be.
There's no question. There's no question.
Okay. No, there will be always a question, Maxime, but it can be trivialized by a theorem. So you say, I know for sure, so that's constant time. So it's polynomial. So that's
yeah, polynomial degree 0, okay, yeah.
so that's okay. So that's okay, okay. So if you tell me, okay, I know that's for sure this, and I will even use such a kind of arguments in my talk. If you know via theorem that you can answer that question in constant time, use it, which is what we call an oracle. Okay, it's a black box. So no problem, we can use that. So I should say, it's difficult to find, you know, good references in that domain. So the people working on that, you know, yeah, so
I didn't get you. You have this number of square roots of permutations. Not every permutation is square root, but some permutations are squares.
But
yeah.
But maybe the question means that you will answer in your talk later. Yeah.
No, this one I won't talk about it. So I won't talk about it, and perhaps we can talk more with Maxime in the, you know, in the. For you, it's trivial, so that's guaranteed that it's positive. That's fair. Okay, so I'm not saying no, but.
So if you pick the identity permutation for h lambda, for
Yes.
then the square you can find sigma squared. So that
Yeah, it's
the
square root
identity.
itself.
Just
Yeah.
take any transposition or the identity itself.
Yes.
So then you have one element in this set.
Yes, indeed.
So obviously it's greater than 0, strictly greater than 0. So deciding is trivial.
Yes, but you see, you have proved something. So this is what I'm saying. You have proved something. So you use that and put it in a computer to decide whether or not the thing, but you have proved something. If you have proved something, so you have a statement. If you have a statement, you use it and implement an algorithm that, and now you have an algorithm. And the second thing, and you say, okay, it's trivial, but I know in constant time that this answer I can answer. So at that moment, you are in P, you are in the class P, what we call P, and there, here, you will put P, and you can be happy, okay? So,
but then we know it's
all right, I should move on, otherwise I will be stuck there.
It is done.
What is?
You know, because you have question marks.
The question mark is because nobody has said it before. So perhaps you will be Maxime as the first answer. So, and that's done. I have no concern about this. Yeah, so that's fair. Okay, that's perfectly fair. I'm not, you know.
It's about question mark.
All right, let's move on. But we will be interested in a variant table. That variant table is the following. So I will lift this problem to the group algebra. Why? Because we have some theoretical physics question that arise with that. All right, good. So this is your group algebra, which means just I'm taking all linear combination with basis, you know, Sn, the elements of Sn. All right, and I will look at a sum over all conjugacy classes of, you know, you sum over a conjugacy class C of lambda, and this is what I call central elements, which are labeled by, you know, the partition. And now, evaluating the character on one central elements, divided by the dimension of your representation, you know, because the character is constant on the class, you just factor out the size of the conjugacy class divided by your dimension, so you have another table. This table is a variant of the first table up to that normalization. You may ask now the same type of question that you have before, and this is what we did here in this paper with Sanjay. So we addressed the column sum, which is the simplest tractable problem that you can do in this setting. You have here the column sums of that chi-hat table now, and you ask for a combinatorial construction for proving that these numbers are non-negative, and then you may ask the question about computing the function, how much does it cost, and deciding the positivity or not, how much does it cost.
But these numbers are rational, not integer.
Okay, so it can be proved that they are algebraic integers as well as rational, so they become simply integers again.
Yeah, I see.
Mm-hmm.
So it's again integers.
Yes,
The row sum is just, there is explicit formula for the row sum.
No, there is no closed form for the explicit. You just have this table, and you sum over all elements, and you're happy with that. So you have two parameters, chi, mu or lambda. If my sum here is a column sum, I'm fixing the partition lambda, and I'm summing over mu's, which are the representations. this is what we call the column sum. If you fix the representation and sum over the this lambda now, well, you have the row sum at that moment.
But it's something like value of the short polynomial at 1.
That's a good question, and indeed you may link them with the Schur polynomial. We haven't been that way anyway, because there are ways to not use that in that simpler setting. Yes, you're right. Okay, let's move on. So where do they come from? Why do we care about these normalized characters? Okay, so they come from a digraph written TQFT on G-flat bundle using the gauge group, G. Think about it as just a finite group at this moment, but we will apply, G equals Sn at some point here. So this is a work by Padalero and many collaborators. And here you see what you do. So first of all, consider again the group algebra of your finite group G and its center. You have two bases there. First of all, the bases which are labeled by conjugacy classes. Again, this is this T mu, guys. And of course, this is just a relation showing you the structure constant of that center. This is C mu nu lambda. And you have the representation basis this time, where you sum over the characters in a given representation and times your vector here. So this is a normal basis of your algebra. So there is an operator that we call creator, Handel creator operator. Why is this? Because you sum over, I'm taking one basis element, the representation basis, I'm summing over it up to a normalization. In fact, if you raise this number to the power h and trace over it, you end up with that number. And when you are a thing theorist, when you see 2h minus 2, you are happy because this is talking about, creating handles on a sphere. And so what you're doing here, this is a partition function of this manifold, which is just a torus with h holes. All right, let's have a look on the boundaries now. So you have another boundary operator that creates boundaries. So you take, B boundaries, and now you label them by, these conjugacy class elements, okay, these central elements. Well, it's like you're creating holes on the spheres. If you compute that partition function, well, you end up with that product of characters. Of course, you can mix both. You want sometimes to have both handles and holes. So you just have to compose these two operators, one th and one t mu's and several t mu's. And this is, of course, the partition function of a surface having h holes, b holes, and h handles. So, of course, then you restrict just to h equals 1 and b equals 1. You go back exactly to the column sum of a character table, which is a variant character table of the symmetric group, the one that I've just discussed before. So these are exactly the column sum of a chi-hat. So asking all computational question, combinatorial question for this column sum is important because it determines also how will you understand your partition function. All right, let's now be careful and define our words, okay? From now on, we have to be specific. So what is a combinatorial construction?
But the numbers you get is something like Hurwitz numbers.
So I'm not sure, okay? So this I cannot tell you if that's Hurwitz number or not. This I don't know. So a combinatorial construction is a construction that will use explicitly, sets and counting procedures. Okay, that should be a mathematical, use mathematical theorem in order to compute that. And only sets. I'm not allow a finite set, sorry. Finite sets, you need this too. All right, so let's have a look. If I'm taking a positive integer, of course I can write it in this way. And of course, f is just a tautology here. So I'm just using f to defining f. So this is not allowed, in this world. Otherwise, it's just trivial. Okay, so let's go back and set up how do you do this. So this is our, what I want to call our master identity. The column sum that we look for is nothing but, the sum over the structure constant of your center of your algebra. Okay, so you have to sum them here. Of course, when you think about it, characters are central elements. They should be talking to the center in some way. So this is the way that you may understand that. But the proof is, starting with the basic relation, you had another t lambda over, you multiply by t lambda, you trace over it by using the delta function. I didn't define the delta function. This is just the delta on the group, where if you select the identity, it becomes 1, otherwise that's a 0. So here, by multiplying these three guys, you are just saying picks all the elements there that multiplies to the identity. So you do this, and then you expand a bit that spot back to conjugacy classes, and then you notice that, in fact, sigma and tau are inverse each other, so they must be on the same conjugacy class if we are in Sn. And this doesn't occur in any group, but in Sn that is. So there is a way of just crashing this delta and this big sum into just the structure constant. So that delta of three central elements is the structure constant times the size of your conjugacy class. Well, then the last thing to do is to expand the delta in terms of characters, and then you can finish the proof. All right. So with this, you have this identity linking you, on one side, the column sum, on the other side, the structure constant of your center. All right, what else? Now let's have a look on deeper in this equation. You are not far, for if you expand the first t mu in what it is, which is a sum over a conjugacy class, you may show that this delta function is in fact constant along that conjugacy class. You just factorize a c mu, which cancels this part, and you back to this. But this is already something that you can interpret. This is exactly counting the number of pairs into two conjugacy classes such that their product with a given element in that conjugacy class goes to the identity. This looks like the equivalent of the Schur-Frobenius relation. Okay, I will come back to that. So you do have already an interpretation of why this number is really counting something, which is particular permutations that multiplies to the identity, provided you pick them within conjugacy class this time. You are not free to choose them in the whole group, but on fixed conjugacy classes. Let me move on. All right, so this is a set. I'm just writing what I said in a set theoretical sense. This is what you have here. Well, the last sum is just to take the union over all partition, and you produce a big set that I call here factorized lambda. Fact lambda. So already you do have one way. What time is it now? 28. Okay, so here we go. So we already have one interpretation of why these variant column sums is a positive integer, and you count it in that way. Okay, as I said, that's just an analog of that thing, but of that counting. But for fixed, it's reducing to the conjugacy classes. Now, in fact, it is in connection with many other scattering. In fact, I will just report two of them. The first is when you do have this triple relation, okay, you can put it in a more symmetric way, in this way. So I'm just, rather than picking one single element in the conjugacy class, I can just enlarge by all element, any element, but I will just have an extra normalization to take care of. So, if you count the number of elements in free conjugacy class such that they multiplies to the identity, this looks like if you say that if tau is factorizes, the inverse of tau is factorizing in two permutations. And this is closely related to Hurwitz's problem of factorizing permutation and Hurwitz's number indeed. But we don't know yet. This connection we haven't yet established. All right. And in fact, this particular factorizing a permutation in terms of two permutation is also very useful in the what I asked a few minutes ago. It's about the Cayley graph, and this is important for sorting algorithms. Okay, so that's important. That's another connection. I don't have any more the time. I have 10 minutes to finish my slide, and I need to show you more. So if you're interested in this, I can tell you more. But it's also related to ribbon graph and maps. And this is what I would like to share with you. So this is where it's, of course, a triple of permutation that multiplies to the identity. We know that, since in the book of Landau and Zvonkin, we know that very much that they are describing surfaces, okay? Bipartite maps, bipartite embedded graphs. So the first one is computing, the cycle of the first permutation is, will describe the cycle, the vertices of the first kind. The cycle of the second permutation will describe the cycle of the second kind. This, this is where the bipartiteness comes from. And then the last permutation will describe the faces of your graph, the boundary of that surface. All right, we know it's immediate since that moment. When we have this free permutation that multiplies to the identity, we're already there. In fact, we are counting surfaces, but not any surfaces, restricted type of surfaces. So we are counting here bipartite ribbon graph of a given type, which means I'm forcing my white vertices, say, to be of a certain type. I'm forcing my black vertices to be of another type, and I'm asking that the length of my faces are of a given type. If you do have such a thing, you count 1. All right. If I'm saying surfaces, I have to talk about genus, okay? So can we talk about genus in the sense? Of course, we can. And you may just, we particularize this sum at fixed mu, and it turns out that if you have, for instance, only permutations mu that describe, if you want, involutions, which means 2 cycles and 1 cycles, you have only that, well, you are guaranteed to have a genus 0 surface. If you want to have more, well, your genus grows a bit like that. Okay. Now we move on to another subject. So far, that was just constructions, counting objects. Now let's move on to yes.
Sorry, I didn't understand. Why do you need to talk about genus in this?
No, I mean, if you want to say we are counting surfaces, how many of those are of genus 0? How many of those are genus 1?
Yeah, but here it seems that you are just counting surfaces without a constraint on the topology, no?
Indeed. Well, yes. I'm just saying if there is just, that's an if there. So I say if you are interested in surfaces of genus 0, here we go. If you are interested in genus of genus 2, there you are, okay? Good. All right, so we discussed about combinatorial constructions. How much is it difficult to get a solution, an answer, okay? So that's a different thing. And in computer science, when you say simple, it means you have a polynomial time algorithm. If it's tough, you say you have an exponential or more algorithm. So now, if you are not aware about, computer science, this is important for you. If you are an expert, I'm sorry, because this is insufficient, okay, to be honest. Okay, so this is a really crash course on what can be, computational classes, but the sense of it is there. Don't worry, you are not far from the true truth. Okay, so you need what we call Turing machines. This is an abstract object in theoretical computer science that is a model of computation, okay? Think about it as a simple computer, okay? That's okay. We call deterministic a Turing machine if it always outputs the same answer for a given input, okay? At any time you give it the input, it gives you the same answer. At the contrary, a non-deterministic Turing machine, if you give it an input, well, you can end up with a set of outputs, okay? So you give it an input, it can give you an answer. You give it the same input, it gives you another. But yet, the set of answers is a finite set. This is what we call a non-deterministic Turing machine. What is the complexity of a computation? So if you fix a given input, it's a number of steps that that Turing machine will do before it ends its computation. So it's depending on the Turing machine, of course, and most of the time, the length of the input. So this is why I put here this absolute value will mean in my talk the length, of the encoding in which you do the X. And this is important, but I will come back to that. So let's discuss the complexity class. I will be interested in only 3 complexity classes in this talk. Is it a hand raising? No. Okay. So P will be the set of decision problem, just yes or no questions that can be answered in polynomial time on a deterministic Turing machine. A NP problem is a set of decision problem, yes, no problem, yes, no questions, that can be computed on non-deterministic Turing machine and ends in polynomial time. P, sharp P, okay, so there is an equivalent definition for NP which is most interesting, and this is what we use in practice. Because I was a bit disappointed because non-deterministic Turing machine does not exist. I mean, theoretically they exist, but nobody can implement them. So all what you have in our real life are deterministic Turing machine. And this, when somebody told me this, I was a bit surprised, but okay. So here we go. This is a way to use Turing machine, deterministic Turing machine, to get your answer. If you can verify a solution in polynomial time using a deterministic Turing machine, you're good. This is an NP problem as well. Sharp P, what's that? Sharp P is a set of functions. Now, it's not yes, no question, but you can have any answer, any positive number answer, such that the decision problem associated with is there an x such that f of x is strictly positive, that guy is in NP. So this is a decision problem. It should be in NP before the function f belongs to sharp P. I hope it's more or less clear. But
I have one question.
Yes.
The second line in your definition of NP.
Yeah.
Is it the same? Where's the difference to P?
Yeah. So here the non-deterministic is important here. Yeah, the first one is deterministic.
The second sentence.
The second sentence. This is verification. So here somebody tells you, I have a yes answer. You say, give me your yes answer. And you check that as yes answer. You have to provide that. Okay, so this is a verification process. Okay, and that's this is a very important question in how much do I have? Am I bad? 37. Yeah. Okay. So it's a very important question to whether checking or producing the answer is the same complexity. All right, let me move on. So the first thing that you have to see is that given lambda, is this quantity positive? Is an NP problem.
Is it now row sum? Yeah.
That's a column sum yet. I'm not addressing the row sum here. It's still the tough problem. So what's the entry? The entry is your partition lambda and its size. Beware. This is I hope Jehan there, he will not. This is not the weight of your partition, but just the size of the encoding. She noted, this is actually, I borrow a bad notation for usual partition here. Anyway, so if you are encoding in unary, which means each number is itself in encoding, well, that size of the partition is, the length is n by itself, because each number is itself, so you add all the numbers and you end up with n. If you encode in binary, well, the size of the partition is bounded by the length of the partition times the logarithm of the maximal part of it. Okay. So that's what it is. So you want to use that construction that we have before to check if this is positive. So what have you to, if somebody say, yes, I do know that this is positive, I ask him, give me your certificate. And what's the certificate here is a triple of permutations and two partitions such that this triple of permutations satisfies some properties. And which are rho and sigma should belong to C mu, tau should belong to C lambda, and you have to check that in polynomial time in the size of lambda. And you have to show that the product of these three permutations goes to the identity in time polynomial of lambda. That's it. Okay, so the lemma 1 will ensure you that this is a case for checking that permutations belong to a conjugacy class. You have to compute the cycle type of the permutation, and this is just computing an orbit. And this is doable in polynomial time. And the second lemma shows you, in fact, that composing two permutation is, again, linear in the size of your permutation, which is n. And this is, again, polynomial, and you are safe. All right. So let me go back to the proof of the theorem. So here, now I use an input. I will use only a unary encoding. So the size of lambda is exactly n in unary encoding in such a way that lemma 1 and lemma 2 are true. And so your problem is in NP, but let's have a look. Now I'm outside of my proof here. What will happen if I have used a binary encoding at that moment? Now you are in trouble because it may happen that your cycle is of length n, that's a big cycle, yeah? And encoding in binary will be like lambda is log of n. And if it's log of n, your permutation are encoded in a list of size n. You are exponential, in that setting, and you're done. So this is going to be wrong. So the problem is NP in what we call unary encoding, and this is important. Yes. Okay. I should. Yes. Okay. So I will be quick here. So the column sum, immediately, because the problem is NP, you can, by a corollary, you can say that this is sharp P. But in fact, you can prove more than that. You can prove that that problem is in P, in fact. You can answer this problem in polynomial time, provided you search a bit and discover that if lambda corresponds to the cycle structure of a permutation which is even, you guaranteed that this column sum is positive. If it's associated with a permutation which is hard, you're guaranteed that it's going to be 0. I use that as an oracle to compute faster. So what you do, in fact, is to produce an algorithm which is taking your partition like that and compute the parity of this cycle in a certain way and output the result. And from that, you immediately know if this lambda, this partition, is associated with a permutation of even type, which is even. And so you shortcut the process of verification. You can just compute the answer. Let me conclude. Okay, so what we've learned is that that column sum, that variant column sum of the character table, normalized by extra factors, actually is, comes from some partition functions of some TQFT that are built over a manifold which is H1, which has H1 and one boundary. We know how to construct a combinatorics around it, which means that we know that how to interpret this and to construct this combinatorially as pairs of permutations such that they multiply to the identity, and that's that number. It also corresponds to some factorization, and then you lastly know that they are, computing also this column sums computes certain number of ribbon graph with some properties. Okay, the complexity class are sorted. We know that the column sums can be computed in a certain way, and it belongs to that class, and deciding this positivity is also easily doable. Future plans. Okay, so far, we don't know how tough it is. We know this problem are in NP and in given class, but is it difficult to evade the most difficult problem in their own class? And this is what we call hardness in computer science, in complexity. All right. So are they Sharpie hard? Are they Sharpie complete? And for that, you need to reduce other problem to them. This is the way we proceed. For instance, is it possible to link them with problem in graph theory that we know that are difficult? For instance, counting Hamiltonian cycles are known to be Sharpie complete. Is it possible to map one problem to the other? We call it reduction. And is it possible to do that? Is the connection with ribbon graph theory is helpful to this we must understand. And then what about the row sum? That's the only difficult problem here. We have solved the easy problem. What about the tough problem? Is this table easier? We don't think so, but perhaps it will lead us to a few differences. So I thank you for your attention.
Thank you, Joseph, for having in time this start many questions.
Yes, I have a question, but I think like maybe your collaborator on Geloun may be interested in kind of concrete questions. So take the surface of genus 5 and groups S1000, yeah, something like this. Can one calculate the actual value of partition function for this data region?
Wow.
That's an answer that probably will be interested in. It's numbers, yeah.
Yes. I think it's certainly a project that try to to understand these numbers as in general, in their full generality. Given two numbers, how do you compute these numbers of cover? Is it your question? Yeah. And to kind of not how can I say, record them in big table, etc. Yeah, that could be fantastic, but they are really tough problem, because you see, when you have this sum over the permutation, it's n factorial.
Yeah, sure, yeah.
And so it's huge as time to compute. So this is the difficulty.
Yeah, but it should be given to this character tables by somehow the rows, columns, sums.
Yes, we hope that. We truly hope that this can be this can be done via a trick using this character table. We think that perhaps it's more tractable looking at that side, but we don't know until we check, right? Mm.
Any other question?
Okay. Thank you very much.